Today we are going to learn how to solve a specific type of Diophantine equation, polynomials with one unknown. A Diophantine equation is an equation where you are only interested in finding the integer solutions. You aren't interested in the real number or complex number solutions. You just want to find the whole number solutions, if there are any. One famous example is the Diophantine equation x squared plus y squared equals z squared. This is a Diophantine equation with three unknowns, x, y, and z. For positive integers, this is just the Pythagorean theorem. Each solution where all the numbers are positive form the sides of a right triangle. For this reason, solutions to this equation are also called Pythagorean triples. There are infinitely many integer solutions to this equation. One well-known solution is 3, 4, 5. Another is 5, 12, and 13. But today we're going to focus on polynomial equations with a single unknown. For example, 2x squared plus 5x minus 3 equals 0. Or 3 times y to the 5th plus 33y to the 4th plus y cubed plus 11y squared equals 2y plus 22. But we will not look at equations like 2 to the z minus z to the 5th equals 17z, since the left-hand side is not a polynomial. This is because the first term, 2 to the z, has a variable as the exponent. Also, we won't consider polynomials like pi x squared plus 3x minus the square root of 2 equals 0, since the coefficients aren't all integers. We're going to focus on Diophantine equations with one unknown where both sides are polynomials and all the coefficients are integers. The first step is to get all terms on one side and rearrange the terms from largest degree to smallest degree. For example, look at the equation 4x squared minus x to the 5th equals 12 minus 2x. If you subtract 12 from both sides, you get 4x squared minus x to the 5th minus 12 equals negative 2x. Next, add 2x to both sides to get 4x squared minus x to the 5th minus 12 plus 2x equals 0. Now all the terms are on one side. This is a polynomial with integer coefficients, but it's not in standard form. Remember, you write polynomials from largest degree to smallest degree. Once we do this, the largest exponent is 5, then 2, then 1, which you don't write, and then the constant term negative 12, which has degree 0. Once our equation is in standard form, we'll check to see if 0 is the solution to the equation. For example, look at the equation 5x cubed plus 2x squared equals 0. On the left-hand side, we can factor out x squared. This gives us x squared times the quantity of 5x plus 2 equals 0. And a key principle in solving equations is that if a product of factors is 0, then one of the factors has to be 0. This is because if you multiply a bunch of numbers together, the only way their product is 0 is if one of the numbers is 0. Once we do this, we see the solutions are 0 and negative 2/5. So this Diophantine equation does have an integer solution, 0. Quick note. When solving a Diophantine equation, sometimes you'll want to find all fraction solutions and not just the integer solutions. In that case, we did just find all the rational solutions, 0 and negative 2/5. But today, we're focused on finding the whole number solutions. For another example, look at the Diophantine equation 3y to the 7th minus 4y squared plus y equals 0. All the terms are on one side, and the polynomial is in standard form. So the first step is done. We can factor out y, which gives us y times the quantity of 3y to the 6th minus 4y plus 1 equals 0. Setting the first factor to 0 gives us one integer solution, y equals 0. But what about the second factor? Is there a straightforward way to tell if 3y to the 6th minus 4y plus 1 equals 0 has an integer solution? You could always graph it and see if it crosses the x-axis anywhere near an integer. The problem with this approach is for very large polynomials, you have to do some work to see how large the graph needs to be sure that you are seeing all of the x-axis crossings. Also, it involves eyeballing the graph, It would be much better to have a simple, fast algorithm that would find all integer solutions. And it turns out that one such algorithm exists. You can write a program to quickly find any and all integer solutions. The key to finding the non-zero solutions lies in one simple trick. And the best way to see this is with an example. Let's find all integer solutions to the Diophantine equation 8x to the 7th minus 2x to the 11th equals negative 15x to the 4th. First, get all terms on one side. Then rearrange them so the polynomial is in standard form. Next, factor out the largest power of x. For this equation, that's x to the 4th. So we know that x equals 0 is an integer solution. But now we have to check the second factor for any integer solutions. Here's the clever trick. Move the constant term to the other side. This means that every term on the left-hand side contains a power of x. So let's simply factor out x. We could factor out x cubed, but to see the trick, we need to factor out just x. Our objective is to find any integer x that's a solution to this equation. This means the first factor, x, needs to be an integer. But if x is an integer, then the second factor, negative 2x to the 6th plus 8x squared, will also be an integer. This is because all the coefficients are integers. So on the left-hand side, both factors are integers. This means that x must divide negative 15. This is the key. All we have to do is make a list of all divisors of negative 15 and check them one by one. Here's a list of all possible solutions. They are all the positive and negative integers that divide negative 15 evenly. If we plug these numbers into the factor negative 2x to the 7th plus 8x cubed plus 15, we get these 8 values. None of them are 0, so we're done. The only solution to the original Diophantine equation is x equals 0. We're now ready to outline the algorithm to find all integer solutions to a Diophantine equation that's a polynomial with a single variable and integer coefficients. Step 1. Get every term on one side and sort them by degree. Step 2. Factor out the largest power of the variable. Step 3. Check all the divisors of the constant term in the remaining factor. You're done. As a final example, let's solve this Diophantine equation. First, move all the terms to one side. Then sort this polynomial by degree so it's in standard form. Next, factor out the largest power of x possible. In this example, that's x cubed. So x equals 0 is a solution to this Diophantine equation. And now we want to check the polynomial in parentheses to see if it's ever 0. To do this, we check all the divisors of the constant term negative 6. There are 8 divisors. 1, negative 1, 2, negative 2, 3, negative 3, and 6, negative 6. If you plug these 8 numbers into the second factor, you get these 8 values. The second factor is 0 when x equals negative 2 or x equals 3. So the solutions to the Diophantine equation are x equals 0, negative 2, and 3.